Okay, welcome to the video on the octet rule. In this video, we're really going to look at using the octet rule to check a couple of Lewis dot structures. But before we begin, I want to talk about what the octet rule is. You should have this in your notes, but it's helpful to have a reminder. The octet rule simply states that atoms in a molecule want 8 electrons around them, and these 8 electrons can come in the form of bonds or lone pair electrons that are directly connected or touching the atom in the Lewis dot structure. And there are a couple of notable exceptions. Hydrogen and boron don't necessarily want 8 electrons, so hydrogen wants 2 only, and boron's okay with 6. So you could see structures where boron has 8 electrons, but oftentimes it just has 6 and it's okay. So we mentioned that when we're counting their electrons, we're counting bonds and lone pairs that are directly touching the atom. It's important to go over what a bond is made of and how many electrons are in each bond. So remember, in a covalent bond, electrons are being shared between the atom. Each bond or each line represented by a single line has 2 electrons. And you can kind of see that here. Like here is an example of a covalent bond. Here's an example of covalent bond, but here's also an example of covalent bond. So this line represents these 2 electrons that are shown here. The lone pairs are the 2 dots that are connected to an atom, connected to one atom only. So notice how that the bonding electrons are between 2 atoms, these 2 fluorine atoms, but the lone pairs are only connected to one atom, and there's a pair of them. Okay, so we mentioned that each bond has 2 electrons. You've also seen single, double, and triple bonds. So remember, the thing to remember is that a single bond has 2. A double bond, which has 2 lines, represented by 2 lines, has 4 electrons. So remember, each line just represents 2 electrons. And a triple bond, of course, would therefore have 6 because there are 3 lines connecting the atom. And each bond or each line has 2 electrons. So 3 times 2 gives you 6 electrons. All right, so now that we kind of went over like sort of counting them by the bonds, and we looked at lone pairs, let's get into an example. You've probably seen this example if you've already watched the video on drawing Lewis dot structures that's listed up above in the playlist, but it'd be helpful to go through it again. All right, so the first thing is after we make a structure, we want to check it to make sure that it's right. One thing to check for is to make sure all atoms have the octet rule. If they don't have the octet rule, that's your clue that you need to go back and fix something. Maybe you skipped a step, like maybe you have some unpaired electrons, or maybe you forgot to put on lone pairs. So that will be your clue to sort of go ahead and fix up your Lewis dot structure. So when we check for the octet rule, we're checking for each atom. And I like to start with the central atom. You don't have to, but that's where I usually start. So in this case, that would be carbon. And what I'm doing is I'm looking at the carbon and making sure that there are 8 electrons that are around it. And again, these are either bonds or lone pairs directly touching the carbon. I notice this carbon has 4 bonds that are directly touching it. So those are the only things I'm going to count. I'm not going to count the lone pairs up here because they're not touching the carbon directly. They are touching the chlorine directly, but not the carbon. Okay. So with that being said, I can go ahead and just count the number of electrons that are actually touching this carbon. So there's 2, 4, 6, 8. Since each bond has 2 electrons, there's 8 electrons around it. And so the carbon's good. I can go ahead and do the same thing with the chlorine now. And I just want to pause here. Notice that there are 2 chlorines, but these 2 chlorines are equivalent. So I only need to check one. What I mean by equivalent is that both chlorines have 1 single bond connected to them and then 3 lone pairs. So they look pretty much the same in terms of counting for octet rule. So I only need to check one of them. If you want, you can check all atoms, but it's usually just better to save yourself some time, and if they're equivalent, only check one of them. Okay, so I'm looking at this chlorine, and I notice that it has a bond and 3 lone pairs that are directly touching it. That means I'm not going to touch the bond over here. I'm not going to touch these. I'm not going to count any of these things. It's just the ones that are directly touching the chlorine. So I can go ahead and start my count. 2 electrons in the bond. That's 2, 4, 6, 8. And that means it has 8 electrons. So again, 1 bond with 2 electrons, and then 6 electrons from the lone pairs. Last thing I'm going to check is the hydrogen, and again, these two hydrogens are equivalent because they both have a single bond attached to them only, no lone pairs, nothing else. I'm looking at this hydrogen and I notice that again it has one bond. Each bond has 2 electrons, so hydrogen has 2 electrons. And that's not a violation of the octet rule because remember hydrogen is an exception, so it wants to have 2 electrons. If I had a hydrogen with 4 electrons or 6 or 8, I would be concerned. That's when I would know there's something wrong with my structure. But since it has 2 electrons, I know that looks good. Let's look at another example where we have a double bond. So once again, I'm looking at the structure. I just made this Lewis structure. I want to check to make sure the structure is good by making sure all the atoms are following the octet rule. Again, I like to start with a central atom. You can start wherever you like, but in this video, we'll start with the central atom. So I'm looking at the carbon and I want to figure out how many bonds or lone pairs or both that are touching it. I only notice that there are some bonds around this carbon. So there's a double bond and then 2 single bonds. So that's what I'm going to be counting. Nothing else is directly touching the carbon. All right, starting with the double bond, each line has 2 electrons, so that's 2, 4. So 4 electrons here, 6, 8. That means the carbon has 8 electrons. There are 4 bonds touching it. 2 electrons each give you 8 electrons. So carbon's good. Now we can move on to the oxygen. Oxygen, again, I'm just focusing on the lone pairs and bonds that are directly attached to it. I've noticed that there are there's a double bond attached to the oxygen and then 2 lone pair electrons. So that's what I'm going to be counting. So again, for the double bond, there's 2, 4, 6, 8. And that means oxygen has 8 electrons, so oxygen looks good. Finally, for the hydrogen, these 2 hydrogens are equivalent, so I can check either one. I'm going to check this one here at the bottom, but it doesn't matter. And remember, equivalent means that this hydrogen has a single bond attached to it, and that's the only thing it has attached to it, and so does this one, so they're equivalent. If this hydrogen had 2 bonds attached to it, they would not be equivalent. All right, so there's that one bond, and there are 2 electrons in each bond, so hydrogen has 2 electrons, which is what we want for hydrogen, since it's one of our exceptions there. So that means the structure is good. All right, so I hope you found this video on using the octet rule to sort of check your structure. I would strongly recommend it because I think a lot of times people make simple mistakes that if they use this as a check to make sure their structure is okay, they'll be able to catch the mistakes before submitting assessments. Anyway, I'll see you all next class. Have a quality day.